From the dropping volt ampere characteristic in some pyroelectric conductors, especially those of high resistance or very high negative temperature coefficient and of considerable cross section, results the tendency to unequal current distribution and the formation of luminous streak at a sudden application of high voltage. Thus, if the current passing through a graphite clay rod of a few hundred ohms resistance is gradually increased, the temperature rises, the voltage first increases and then decreases with the rod while the rod passes from range 2 into range 3 of the volt ampere characteristic, but the temperature and thus the current density throughout the section of the rod is fairly uniform. If, however, the full voltage is suddenly applied, such as by a lightning discharge throwing line voltage on the series resistances of lightning arresters, the rod heats up very rapidly, too rapidly for the temperature to equalize throughout the rod section, and a part of the section passes the maximum voltage point B of figure 4 into range 3 and 4 of low resistance, high current, and high temperature, while most of the section is still in the high resistance range 2 and never passes beyond this range, as it is practically short-circuited. Thus, practically all the current passes by an irregular luminous streak through a small section of the rod, while most of the section is relatively cold and practically does not participate in the conduction. Gradually, by heat conduction, the temperature and the current density may become more uniform. If before this the rod has not been destroyed by temperature stresses, thus tests made on such conductors by gradual application of voltage give no information on their behavior under sudden voltage application. The liability to the formation of such luminous streaks naturally increases with the increasing heat conductivity of the material, with increasing resistance and temperature coefficient of resistance, and with conductors of extremely high temperature coefficient, such as silicates, oxides of high resistivity, etc., it is practically impossible to get current to flow through any appreciable conductor section, but the conduction is always streak conduction. Some pyroelectric conductors have the characteristic that their resistance increases permanently, often by many hundred centimeters, when the conductor is for sometimes exposed to high frequency electrostatic discharges. Cohere, cohere action, that is, an abrupt change of conductivity by an electrostatic spark, a wireless wave, etc., also is exhibited by some pyroelectric conductors. 13. On page 19. Operation of pyroelectric conductors on a constant voltage circuit and in an unstable breach, number 3, is possible by insertion of a series resistance or reactance in alternating current circuits of such value that the resultant volt ampere characteristic is stable, that is, rises with increase of current. Thus, the conduction in figure 4 shown as 1 graph 1 in figure 11 in series with metallic resistance giving characteristic A gives the resultant characteristics 2 in figure 11. So in 4 shown as number 1 in figure 11 in series with the metallic resistance giving characteristic A gives the resultant characteristic in figure 11 characteristic 2. Um, just a sec. Okay, continuing. One in series with a smaller resistance of characteristic B gives the resultant characteristic 3. In this, the unstable range has contracted from B prime to C prime. Further discussion of the instability of such conductors, the effect of resistance in stabilizing them, and the resultant stability curve are found in chapter on instability of electric circuits under arcs and similar conductors. It is doubtful whether the pyroelectric conductors really form one class, or whether by the physical nature of their conduction they should not be divided into at least two classes. Number one, true pyroelectric conductors in which the very high negative temperature coefficient is a characteristic of the material. In this class probably belong silicon and its alloys, boron, magnetite, and other metallic oxides, sulfides, carbides, etc. Number two, conductors, which are a mixture of materials of high conductivity and non-conductors, derive their resistance from the contact resistance between the conducting particles, which are separated by non-conductors. As contact resistance shares with arc conduction the dropping volt ampere characteristic, such mixture thereby imitate pyroelectric conduction. In this class probably belong the graphite, clay rods industrially used, powder of metals, graphite, and other good conductors also belong in this class. The very great increase of resistance of some conductors and the electrostatic discharges probably is limited to this class and is the result of high current density of the condenser discharge burning of the contact points. Coherent action probably is limited also to those conductors and is the result of the minute spark at the contact points initiating conduction. Carbon 15, in some respects outside of the three classes of conductors thus far discussed, another intermediate between them is one of the industrially most important conductor, carbon. Volt ampere characteristic of carbon. It exists in large variety of modifications of different resistance characteristics, which all are more or less intermediate between three typical forms. Number one, metallic carbon. It is produced from carbon deposits on an incandescent filament. It is produced from carbon deposited on incandescent filament from hydrocarbon vapors at a partial vacuum by exposure to the highest temperatures of the electric furnace. Physically, it has metallic characteristics, high elasticity, metallic luster, etc. And electrically, it has a relative low resistance approaching that of the metallic conduction and a positive temperature coefficient of resistance, or about 0.1% per degree Celsius, that is, of the same magnitude as mercury or cast iron. The coating of the gem filament incandescent lamp consists of this modification of carbon. Number two, amorphous carbon is produced by the carbonization of cellulose in its purest form as produced by exposure to the highest temperatures of the electric furnace. It is characterized by a relatively high resistance and a negative temperature coefficient of resistance in its conductivity increasing by about 0.1% per degree. Anthracite is an extremely high resistance. It's practically an insulator but has a very high negative temperature coefficient of resistance and thus becomes a fairly good conductor at high temperatures, but its heat conductivity is so low and the negative temperature coefficient of resistance so high that the conduction is practically always streak conduction, and at the high temperature of the conducting luminous streak, conversion to graphite occurs with a permanent decrease of resistance. One, this shows the characteristics of metallic conduction. Number two, those of electrolytic conduction. And three, those of pyroelectric conduction. Figure 12 shows the volt ampere characteristics, and 13 the resistance temperature characteristics of amorphous carbon curve 1 and metallic carbon curve 2. Hmm. Resistance temperature characteristic of carbon resistivity in ohms per centimeter resistivity and approximate temperature. Insulators. As fourth class of conductors may be considered the so-called insulators, that is, conductors which have such a high specific resistance that they cannot industrially be used for conveying electric power, but on the contrary are used for restraining the flow of electric power to the conductor or path by separating the conductor from the surrounding space by such an insulator. The insulators also have a conductivity, but their specific resistance is extremely high. For instance, the specific resistance of fiber is about 10 to the 12, or mica 10 to the 14, or rubber 10 to the 16th of ohms per centimeter. Therefore, the distinction between conductor and insulator is only qualitative, depending on the application and more particularly on the ratio of voltage to current given by the source of power. Sometimes a material may be considered either as insulator or conductor, as when dealing with electrostatic machines, which give high voltages by extremely small currents, wood, paper, etc., are usually considered as conductors, while for the low voltage, high current electric lighting circuits, they are insulators. And for the high power, very high voltage transmission circuits, they are on the borderline, are poor conductors and poor insulators. Insulators usually, if not always, have a high negative temperature coefficient of resistance, and the resistivity often follows approximately the exponential law R equals R0 e to the minus A times T, where T is temperature. That is, the resistance decreases by the same percentage of its value for every degree. For instance, it decreases to 1/10 of every 25 degrees Celsius rise of temperature, so that at 100 it is 10,000 times lower than at 0 centigrade. Some temperature resistance curves with log R as ordinates or insulating materials are given in figure 14. As the result of the high negative temperature coefficient for a sufficient high temperature, the insulating material, if not destroyed by the temperature, as is the case with organic materials, becomes appreciably conducting, and finally because it becomes a fairly good conductor, usually an electrolytic conductor. Thus, the material of the Nernst lamp, rare oxide, Nernst lamp, rare oxide similar to the Welsbach mantle of the gas industry, is a practically perfect insulator at ordinary temperatures, but becomes conducting at high temperature and is then used as light giving conductor. Figure 15 shows for a number of high resistance insulating materials the temperature resistance curve at the range where the resistivity becomes comparable with that of other conductors. 17. Many insulators, however, more particularly the organic materials, are chemically or physically changed or destroyed before the temperature of appreciable conduction is reached. But even these show the high negative temperature coefficient. With some, as varnishes, etc., the conductivity becomes sufficient at high temperatures, while still below carbonization temperature, that under high electrostatic stress, as in an insulation of high voltage apparatus, appreciable energy is represented by the leakage current through the insulation, and in this case, rapid I squared times R heating and final destruction of the material may result. That is, such materials, while excellent insulators at ordinary temperature, are unreliable at high temperature. It is quite probable that there is no essential difference between the true pyroelectric conductors and the insulators, but the latter are merely pyroelectric conductors in which the initial resistivity and the voltage at the maximum point B are so high the change from range 2 of the pyroelectrolyte figure 4 to the range 3 cannot be produced by increase of voltage. That is, the distinction between pyroelectric conductor and insulator would be the quantity for one. That in the former, the maximum voltage point of the volt ampere characteristic is within experimental reach, while with the latter it is beyond reach. So we have figure 14. So with degrees Celsius from 10 to 150 every 10, and resistivity on a logarithmic scale. No, this is logarithmic. Every 10. Raw linseed oil. Quite resistive. The highest resistivity, yellow varnished cloth, special varnished cloth, transil oil, black varnished cloth. Voltage point, okay, whether this applies to all insulators or whether among our organic compounds as oils, there are true insulators which are not pyroelectric conductors in certain. Positive temperature coefficient of resistivity is very often met in insulating materials such as oils, fibrous materials, etc. In this case, however, the rise of resistance at increase of temperature usually remains permanent after the temperature is again lowered. Resistivity temperature characteristic of high temperature insulators. So horizontal is the temperature up to 1,000 degrees. Pure river water up to 100 degrees, obviously, is 4, I think, ohms centimeter. Now, boron nitrate, very high temperatures. Lava, porcelain, quite steep drop of from 6 to 4. Interesting. And the apparent positive temperature was once again. In this case, however, the rise of resistance at increase of temperature usually remains permanent after the temperature is again lowered. And the apparent positive temperature coefficient was due to the expulsion of moisture absorbed by the material. With insulators of very high resistivity, extremely small traces of moisture may decrease the resistivity many thousandfold, and the conductivity on insulating material very often is also entirely moisture conduction, that is not due to the material proper but due to the moisture absorbed by it. In such a case, prolonged drying may increase the resistivity enormously, and when dry, the material then shows the negative temperature coefficient of resistance incident to pyrolytic conduction.